Good morning. This is Miss Dagenford, and we're going to be continuing our discussion on the oxygen hemoglobin dissociation curve. Now, this graph at first can be really, really frustrating to look at, and it's not as bad as you think. What we see is the y-axis and x-axis that's the most frustrating, is understanding what the y-axis and x-axis are referring to. The y-axis is typically called the oxygen saturation, how saturated hemoglobin is. And so, for instance, way down at the bottom of the y-axis, if we were to look at hemoglobin, hemoglobin would have very little oxygen. In other words, it would be unsaturated. It would not be saturated. Up here on the top of the y-axis, we would see that hemoglobin would be fully saturated. It would be full of oxygen. Now, the way to understand this is that this is a measure of the affinity for hemoglobin for oxygen. So this is the hemoglobin affinity for oxygen. And then we can go with, we understand what affinity means. Affinity means that we like something. So if we have a high affinity, then we're going to grab the oxygen. And so up here on the top of the y-axis, we're going to have a fully saturated hemoglobin because it has a high affinity. Down here at the bottom, we would have unsaturated hemoglobin because it has a very low affinity. So on graphs, you're going to see it as a saturation, but you want to look at that and understand that this is the affinity for hemoglobin to oxygen. Now down at the x-axis, we're going to see the partial pressure of oxygen, the PO2. And so that's how you want to look at it. If you see PO2, that means the partial pressure. And this is a measure of the relative amounts of the gases. But again, what we want to look at it is really, this is referring to the amount of oxygen. Up here, this would be 100%. And then down here, this is 40%. Down here is somewhere around 20%. And the way you want to look at this is corresponding it to the body. For instance, where in the body do we see 100% of oxygen? Well, you might very correctly be thinking that that would be the lungs, because that's when we're breathing in the oxygen that is, compared to the rest of our body, 100% oxygenated. And then down here at 40%, this is a cell at rest. So this point right here is a cell at rest. And then down here, we would see maybe a cell that is exercising. In other words, a cell that is needing, like a muscle cell that is quite depleted of oxygen because it's using oxygen. So if we put these two together, what we notice is that way up here, there's a couple of points to really notice. Up here in our lungs, in our alveoli, to get a little bit more precise, we see the fact that hemoglobin has a high affinity. And that's going to be really important. So hemoglobin has a high affinity for oxygen. And the way to think about that would then be that it grabs oxygen very well. It has a very good binding for oxygen. Now, if we start to drift down, maybe at the 80% level, It does lower a bit, but there's something very interesting about this part of the graph. It has a very low slope, and this low slope is going to be very helpful for us because that means you can have a relatively large change in X without having a big change in Y. Very simple math lesson there, last math review. And so notice we've changed by 20% of oxygen, but we really have only changed a little tiny bit for the affinity. Think about the implications there. If we're looking, for instance, at going up into the mountains, even though the mountains might be low in oxygen, we still want hemoglobin to bind pretty well. Now, we're going to feel it. We're going to feel that lack of oxygen. Uh, but imagine, if you will, what if this were not that S-shaped curve, but a linear curve? That 20% difference in just going up the mountains would result in a big drop in affinity for hemoglobin oxygen, and that would be disastrous for us. So we like this S-shaped curve. This S-shaped curve is going to be work wonderfully for us. Now, right around this 50, 60% mark, we see that curve start drastically changing. It switches. And we then see on the bottom half, we see a higher slope. And a higher slope is going to be, again, really helpful at the tissues of our body. The tissues of our body, these are going to be the ones that are using oxygen. And so they need oxygen. And what we're looking at then is hemoglobin. Hemoglobin then starts to lose its oxygen. The oxygen unloads. So hemoglobin starts unloading the oxygen, and it does so pretty quickly. And that is represented by the slope change. So this S-shaped slope is very, very important. So it unloads the oxygen and unloads it relatively fast. So what I've used the analogy that hemoglobin is a kind of a multiple personality molecule. It can be very, very greedy up top here and grab onto oxygen, but then real quickly it's going to be very generous and lose that oxygen for the tissues. And then we can even look down here at a cell that is really depleted of oxygen down at 20%. Hemoglobin is even less um, likely to hold on to the oxygen. It releases it. Now I'm using greedy and generous, which is really, kind of nice to understand it, but let's think about the fact that this means that there are changes that are occurring in the molecule. There are changes that occur in the shape of the hemoglobin that help it to release the oxygen. There are changes to the chemistry of the hemoglobin that make it release oxygen. There is a molecule called bisphosphoglycerate, BPG, and BPG will bind to hemoglobin at low oxygen levels. And this is a bit of a positive feedback because once it binds to hemoglobin, it will actually cause more oxygen to release. And that's going to be really helpful for us because it means that there's going to be more oxygen released to the tissues. This happens at low oxygen levels. And so that is the basics of the oxygen hemoglobin dissociation curve. Now there's an application to this, and that is when we exercise and exercise will cause it to shift. Well, a lot of books will call it shifts to the right. This would be the normal blood pH, like 7.4, and then the solid line would be 7.2. I like to think of it as it shifts down, though, and the reason for it is when you exercise, your blood pH ever so slightly changes. The pH decreases, becomes slightly more acidic. Now we would never, I mean, going from pH 7.4 to 7.2, we would never notice it, but our body does. We do not want it to change too much. So going back to this tissue at 40%, well, when we start exercising, we are producing more carbon dioxide, and more carbon dioxide that will be changed to an acid in our bloodstream, and that's what causes the decrease in pH. Well, this will cause the hemoglobin's affinity to decrease. Now, remember, the y-axis is the hemoglobin saturation, and we can think of that as the affinity for hemoglobin to oxygen. So 40%, this would be at rest, this would be exercising. Notice it's gone down from 7.4 to 7.2. The hemoglobin's affinity goes down. In practical terms, this means it is releasing more oxygen, which is exactly what we want. Now, up here on the top, we do see a decrease, but it's not as much because of that low slope. But we really see it down here with the tissues. We want that change to happen. We want more oxygen to be released. Increasing the temperature will also cause this to happen, as well as increasing BPG, that bisphosphoglycerate molecule. We are going to be looking at different variations of hemoglobin in the next series. Thank you.